Okay, good morning. We're going to continue with CT. We have basically this lecture, then one more lecture that'll be sort of advanced applications of CT before the midterm. I talked to Elizabeth, I think, and there were some questions about this quiz that's coming up, quiz number 1. Would it be more like the quiz from 2018 or the quiz from 2017? Those two quizzes are fairly similar, except for in 2018 there's a question, it's obviously from Tom, it's the first question about magnification and the projection of a rect function. We didn't do magnification this year, so that you won't need to know about that stuff. But otherwise, those two quizzes are pretty representative. Any other questions from last lecture? Anything from Monday? This was in here at Wednesday. Okay, great. So the question came up a couple of times. It's a natural thing to ask is like, what is the requirement for sampling? Since we've discussed the adequacy of sampling at a specific rate to avoid aliasing, and therefore in a CT scanner, what rate do you need to sample? Both along a projection, and how many angles would you need to make a picture that has adequate resolution and a lack of aliasing artifact. In the early days, remember, of CT, there was one detector, and you slid this detector along one dimension. And so you painted out a one-dimensional GL theta by sliding this detector along. And so, you could stop it at an infinite number of locations along here, or you could do it continuously, right? What's going to essentially determine your resolution in this direction and under those conditions? Anybody have a feel for what would make for a higher or lower resolution as I'm taking my detector along this way? Right, well, we can sample, let's say we sample every 50 microns, so that's a really high sampling rate, right? We're going to stop every 50 microns, take a measurement, stop every 50, like that. So that's one thing. What else could affect it? Say it. The size of each detector? Right. In this case, we have one detector. Okay. So just like the size of that detector. If that thing is a centimeter wide, it's going to integrate signal from, visualing up from a centimeter wide, right? So the detector itself has to be narrow, right? So the dimension of that detector has to be narrow. So that's going to sort of set a sampling in this direction. And in the frequency domain, if I have that, detector that's a rectangle like this, what do you think is happening over in the frequency domain, if we think of it that way? All right, so we have a right. It's going to roll it off, right? Because it's as the rect gets wider in the frequency domain, the Fourier transform of that thing, gets narrower and narrower. So higher frequencies get attenuated. Okay, so just to first order on a one-dimensional function. Now we saw in CT, because we're doing these polar projections, it doesn't actually work out that way for CT when you're doing back projection imaging. But in a one-dimensional case, if all we were doing is a one-dimensional function, that's a simple way to think about it. Is that a wider rectangle function gives you a narrower bandwidth in Fourier space in that 1D, right? So yeah, we have the width of this detector. So we make this thing 50 microns wide, so it's looking at a very narrow line through the sample. And then we also discussed, but we didn't do it in detail, the fact that unless the X-rays are coming from a point, we have a problem in that we could have X-rays, say the X-rays are coming from a very wide source. The X-rays from over here can be passing through, hitting our detector. X-rays from over here can be passed through and hit our detector. So that also blurs the picture, and that's the spot size. So we don't raster a single detector anymore. We have a fixed set of detectors, and in fact, we have a fixed set of two-dimensional fixed set of detectors. So it's just like a camera, right? We're going to take a picture that way, and the separation between these elements kind of sets our sampling frequency in the L direction with GL theta, right? So that's already set for us by the manufacturer. Unfortunately, we can't dial it and like shift them down, shift them up, right? The way these things are designed right now, 99% of CT scanners that are sitting in hospitals right now, the separation between these pixel elements, or sometimes they're called detector elements or dexels as opposed to pixels, the separation between those is usually about a millimeter, plus or minus 10%, right?
Bring down the sampling rate.
Say that again?
We'll still be able to bring down the sampling rate. The maximum sampling rate is fixed for a particular device.
So the question is, can we bring down the sampling rate? Is that the question? Yeah, okay. So our sampling rate is fixed by this separation, but we can average these neighboring pixels together, or dexels together, and that will bring down the sampling rate. So you can, just combine every two, and all of a sudden your sampling rate's cut in half, right? And the estimate of the number of X-rays you're getting is improved when you combine two together because you're averaging, right? But you get a blurrier picture. Okay? So that's true. You can drop the sampling rate. So there's some Matlab code that you have, actually. This is the stuff that you have to play around with. And you can look at the effect of either changing the sampling rate in L, so that would be the number of points, of data points that you're going to choose before you do your inverse radon transform. So the way that program works is you just have a picture, you get the radon transform that is like the truth, right? So you sample it highly, get a high sample radon transform. You subsample that radon transform and bring it back with inverse radon and see what happens when you subsample, right? And so when you subsample by dropping the number of views total number of views that we'll use to make a picture, so we take our radon transform and then we take only, say, 45 views through that raw data and bring it back, you start to see these artifacts, right? And this is undersampling in the theta direction. It's characteristic of most CT images. When you see an artifact in a CT image, a lot of it are these radial streaks off things. And it's not that surprising because we're doing all of this back projecting. So if we have something that's abnormal, you're going to see a streak through the picture. The one thing, unfortunately, on the problem set, I forgot that you didn't have noise on your data on the problem set. So that's going to be fixed this week. You're going to get a problem set with some noise on it. So like resolving two things and everything was kind of a simple problem. But when you have noise in the raw data space, so this is the sinogram, or the radon transform of these little squares. The radon transform looks like this. And if you have noise over here because of X-ray counting statistics or because of electronics, the electronics just have noise, then when you take the inverse radon, you'll get this picture versus this one. And so this is what the picture looks like when there is random noise added to your raw data. So it's more a realistic situation, is that this data actually has some variability on it from noise processes. Okay, so this is the noise-free inversion with only 45 views, and this is with noise added. You can see the artifact is basically the same. You get this X-ray stuff, although you're starting to get some extra ghosting images here with that noise added on there. Okay, so that's 45 views. That's 90 views. So we just add an extra view in between each one that we had before. Let's do that again. So watch the center thing here. This is 45 views, 90 views, 180 views. Okay, so the image is getting more realistic with each one, right? Let's do it again. So it's 45, 90, 180. So we just doubled the number of views each time there. So we're getting to the point where we're probably adequately sampled, you think, right? It looks like the pixels in this region of the image look relatively, symmetric, and they have a sort of standard noise look to them. Whereas over here they had this funny streaky pattern everywhere. There's patterns in the background that aren't there. That's artifact, right? Here, this just looks like noise in the background. There's no structure there that you would say is just a wrong picture, right? But what's interesting, though, those of you who have keen eyes for image quality and things like that, is it's not your glasses, right? And it's not your eyeball. It doesn't look as good out here as it does in here, right? Now, oftentimes with optics, you'll see, that the center of the lens is just performing better than the edges of the lens, right? And when you get a cheap pair of binoculars and you put it in, you can see that off to the, borders of the picture, things are starting to blur. And so there's something going on here about image quality in the middle of this versus image quality on the outside. And this is essentially what is being determined by our sampling rate in theta. What's being determined is what is the field of view within which we are adequately sampled to make this picture. Right? You can run through all of these different things with the program, and I find it useful to have this text up here so that when you just capture it on your computer, if you're putting pictures in as an answer or something like that, you know exactly what the parameters were that you ran, as opposed to just like, where did this come from? So that's why this window is there as well. So there's 360. So 360, it looks like we're going all the way out, right? The other thing that's happening is it seems like the signal to noise as we move forward seems to be getting better, right, when I go to 360, and that makes sense. So we're just adding more data into this, the creation of this image. So 720, now it just looks like we're dropping the noise in the background when I go from 360 to 720. Right? Okay. So the question now is, what's going on inside, this circle, inside which the noise field looks normal and the image looks like the correct resolution, and out here where I've got still some artifact and some blurring going on. So this is a 256 by 256 pixel image, right? And it has been reconstructed using 180 degrees or 180 projections, right? And so they're 1 degree apart through 180 degrees. And the question is, inside this picture, what field of view has been adequately sampled? And it certainly looks like it's a circle about this big, right? Because this stuff still looks artifacty and it's blurry in this direction. So this is called view aliasing and or undersampling. So if we have a point object, and so this is basically our point spread function along GL theta from our sampling, right? We then convolve it with either the inverse Fourier transform or the ramp if we're just going to do it with no filtering, or the inverse Fourier transform of like a Hamming filter, which smooths it out, remember we saw these kernels get a little smoother. But we project all these things back, and we start seeing this interference pattern between the side lobes of this. And when we're undersampled, we obviously get streaks out here in the periphery. But right in the middle, we're starting to see the buildup of a reasonable picture, right, early on with just a few projections. But it's going to take a while to build up the picture out here. So it's just a sort of common sense way to think about it. And this is from a classic book on CT reconstruction by Kagan-Slaney, where they plotted what the picture looks like when you look samples per projection. So this is along the L direction, like how frequently we're sampling in that direction for GL theta. And here we have 512 samples along the L direction, and this is 64. And this is the number of projections used to reconstruct the picture. And you can see the picture is just an ellipse here. And so with very few samples in L and very few projections, we get this, significantly underestimated or artifact containing picture where we have large streaks here. When I have a lot of samples in L and many projections matched, I get a reasonable picture, and there seems to be some kind of circular region here. So I need to match these two things, actually, right, to get where I'm going. And you get these complex aliasing patterns for different levels of undersampling in either L or theta. So let's go back about 4 lectures and remember what it means to sample adequately. Okay? So if I have a sine wave, a signal that's oscillating in space, and I need to pick up that oscillation, I don't want it just to get blurred out as an average, right? I need to sample it frequently enough along that direction in order to see the oscillation, right? And so from a common sense viewpoint, I need to sample at least one point when I'm at a peak, one point at a trough, one point at a peak, one point at a trough, right? If I sample with a higher frequency, I do represent that function well enough, right? This is the cutoff at which when I have, say, the spatial frequency of 1 cycle per millimeter and my delta spacing here is a half, then I start getting this full cycle, right? So 1 up, 1 down, 1 up, 1 down. And that's the Nyquist sampling criterion. So the way to think about the projection, convolution back projection, is that we need to sample at the Nyquist criterion in the theta direction as well. So if I have a picture and I look along the theta direction, or an arc along the theta direction, and I have a spatial frequency along that arc, I need to sample at a high enough spatial frequency to rebuild that signal, right? And as you can imagine, as we get farther and farther out, the structure of the polar sampling is that the samples get farther and farther apart, right? And so it turns out, and we'll derive this, that you can actually determine, once you know that you have a number of views, what diameter, inside that diameter, you're going to be adequately sampled to not have aliasing, and outside that diameter, you'll have artifacts in the picture, okay? And it turns out that it's a factor of pi over 2 times the number of projections, or number of projections divided by pi over 2. So for 180 projections in this instance, the diameter I can achieve is 115 pixels. And we'll see how we derive that. So here's just some appearance of aliasing artifacts. This is the true object. if we have noise, you get streaks in the image off various edges of the image. Right? This is if I have too few samples along L, I'll start seeing these kind of structured aliasing artifacts off the edge. And when you have an inadequate number of views, you don't see the aliasing until you hit some critical radius, right? At which time you start seeing these streaks. Right? So how do we derive this? So if this is the L direction, and we're taking a sample, say every 1 millimeter in our sampling, on the sampling array, and then I rotate to get a new angle and get a new set of samples, then in space I have a distance between this sample and this sample. Right? Along this direction, I know precisely what my sampling rate is. The sampling period is delta L, the sampling rate is 1 over delta L. And then when I add theta and go this way, I can calculate what my sampling distance is at the sort of extreme part of my sampling grid. And really, it boils down to a very simple fact, is that we want delta S, we want enough angles and theta to be a value such that delta S is equal to delta L. Okay? And so you can see for a specific theta, that criterion will occur at different radii. Right? So when I'm at a point where, say, delta L and this are the same distance, then I'm inside that field of view that is adequately sampled. Right? So it's pretty intuitive. We can do a calculation to figure out where this occurs and how many views you need for this to be adequate. So here, if we call this our field of view, that's our target here, which is just the whole array across L, right? So that's just a real number, field of view, and it's the number of points along L times delta L is just in centimeters or millimeters, whatever. And we know that delta S, right? We can compute what delta S is just by knowing the circumference of a circle, right? So we know what this distance is, right? Given the fact that we know the field of view, we can just compute that distance, and it's associated like pi over 2. And then we have an equation that tells us the relationship between delta S and the number of angles that we've taken, right? So if we set the criteria that delta S and delta L are the same, right, the number of views required for that is the number of views along here, number of projected views times pi over 2, right? So it's like 1.54 or whatever to obtain that. So if I have 100 here, I need about 150 views, right? Another way to think about it is, suppose instead of thinking about it in this polar space, we look at what's going on in Fourier space. We know from the projection slice theorem that in Fourier space, the Fourier transform of this projection just sits here in space, and the Fourier transform of this projection sits here, right? If we want to adequately invert this function, right, with an inverse Fourier transform to go back to our picture, we need to be able to interpolate the data that we've measured onto this rectilinear grid, right? And the delta kx here gives us the dimensions of the field of view, or the replicants of the image. Right? So in order to adequately interpolate onto this grid, you have to have a reasonable distance between these points. Right? And so out here, for example, if I needed these two values, the closest values I have, if the other angles down here are pretty far away. Right? And so I'm going to have to do a lot of lengthy interpolation and smoothing to figure out what the data is in here, and I'm undersampled out here. And so that's going to give me artifacts. And so that's thinking about it in the Fourier domain, but given this relationship, we can think about it just in the spatial domain. If you're willing to believe that in order to measure up a function that's oscillating as I traverse theta, I basically want to measure it at the same rate that I'm measuring oscillations in the radial direction, right, to match those two directions. Okay? It's one of those things that's common sense, right? But you know, there's a lot of things in math that when you look at them, they're not common sense, but it seems to work out. Okay, so if we look at the quality of CT images, now you can start looking at them with a slightly different eye, and that is, you know, regardless of how this image was obtained, you know that the stuff in the middle is of higher fidelity than the stuff at the edges, right? Because the stuff in the middle is just sampled with you know, a higher rate, right, than this stuff out here. And so when you look at a picture, it now becomes pretty obvious, right, that the characteristics of that signal right there, the sort of white noise background of that signal, is quite different than the characteristic of that signal. Because you can see there's this kind of correlated, you know, streaky type of signal that's going out radially here, and that is not in the phantom, right? That's not what water looks like. It's not flowing radially outward or whatever. It's just it's this stuff. So this occurs for all CT images, and so if you're interested in imaging something with high resolution, you should probably put it in the middle of the scanner, right? Regardless of how you're going to image this darn thing, put it in the middle of the scanner because it'll get sampled the best, right? So this is, it's interesting to look at the dynamics of CT noise as well. So these are just basically slices through a phantom, right? So we're just taking one image, moving a millimeter, taking another image, moving a millimeter. The phantom doesn't change, right? So all the signals are the same, and this shows you the sort of stability of the noise, right? And you can see there is kind of a structure, not only to the spatial structure, but also there seems to be a temporal structure, which in this case turns out is a spatial structure in Z, because we're moving through the phantom in Z, right? So in here, you sort of see like a roiling random signal that is kind of bubbling up or bubbling outwards, whereas here it seems to be rotating or shooting outwards. And this is why CT signal-to-noise analysis is a little tricky, right? Because it's not just a noise field that is like white, ergodic, Gaussian noise. It has structure, right? And so you're competing with this noise structure when you're trying to detect things. And so it's interesting. This is unlike noise in standard MRI. Standard MRI, when you don't use some crazy acceleration technique or something, the noise is just basically white. It's Gaussian, all frequencies are represented, and it's really clean. Here, this noise is kind of complicated. It also tells you that the point spread function, remember what the point spread function characterizes the spatial resolution of a system. The point spread function in CT is going to be different here than it is over here, right? So it's not basically, you can't just translate that point spread function and move it out to here. When you're looking at characterizing a system very explicitly, the point spread function or modulation transfer function is given as a function of position in here, which is something that is not, there are thousands of papers written where that is not taken into account, but that's the state of affairs. So in creating images, you get to modify, to a certain extent, the raw data. So if we go back, let's see what I got here. If we go back to here, okay. This is our raw data, right? And so when we're performing an image, we don't start here, right? Because we do when we do a simulation like this Matlab program, because I want the true image here. But what happens when we go to the scanner, we take a picture, we have this. We don't know what this is, right? So we have this. Now if you looked at this data and you said, oh man, I got to improve this image because things are really crappy here. Somebody tell me what's the first thing you would try and do to improve this data to make your picture?
You take like a non-phantom image and then subtract it from this image.
That's an interesting proposal. Okay, so let's take an image in which everything is just blue in the background because there's nothing in the field of view, so that's an air image. And we'll subtract that from this picture. And that's an interesting proposal. If there was some kind of amplitude structure back here that you wanted to get rid of, that was there in the air image, then yes, you would do that. You could do that, or you could even divide by the air image, right? To try and make it constant. So that's a good proposal if I had some kind of variability in there I wanted to get rid of. Is there variability here, do you think? Doesn't look like it, right? So how could we, what else could we do to try and improve this data before we do our reconstruction? Is the variability along this line, if I draw a line here, say I draw some random line, like that one, so that would be like a pixel, you know, at a specific point in the image would be a line in the sinogram, right? So I draw along that line. Are the if it goes through here, are the values as I'm clicking along here, they're changing? Is that an actual object? No. All this crap is noise, right? That's just noise. And so the only thing this stuff's going to do is give you variability over here that is just noise, right? So often what manufacturers do is they look at their raw data and they get swaths of real estate in the raw data that look like they should be smooth, and they smooth them, right? And basically make the executive decision that, you know what, this area of the data shouldn't have, you know, high, you know, frequency oscillations in it. It should be smooth, and they'll smooth it, and they'll do that at different locations in the data depending on what the data looks like.
So how is that done usually? How do they smooth it out? Do they apply certain filter?
That's exactly what they do. So if they might draw a box like this and say everything inside that box is going to be the average value inside this box, and so the whole patch would be that value. And so now all the variability is gone. It's in that box, and that's just a simple convolution of some box, right? Yeah.
I'm sorry, is that similar to like thresholding?
Well, I mean, thresholding is a very nonlinear filter in the sense that you say everything above this, I'm just going to plank it back down to here, as opposed to a smoothing, which is you just average everything inside the box, And because that's a convolution, that's a linear filter, and it behaves sort of in a predictable way. A lot of nonlinear filtering is done in CT, actually, which gives us much different looking pictures.
We may also try out a sliding window approach wherein we try to find the variance within that sliding window. And if the variance is higher, it means there's actually a signal in it.
Yep.
And otherwise, it's noise and it can be filtered.
That's exactly right. So if I have my box and I'm sliding along like this, and I just get the same statistics over and over and over again as I'm sliding, just do the average. As my box goes down here and I go, whoop, wait a minute, I don't have the same statistics anymore, right? So I'm not going to apply this global average, I'm going to adapt. And so that's principally what they do. They look at the data with the variance and gradients and all sorts of things, and then decide what to do with that data. And it gives us a very interesting phenomenon, which is this. This is an axial image through the heart of a human. And to get you oriented again, because we haven't looked at these in a while, this is the patient's chest here. This is air above their chest. This is air in their lungs. Left ventricle, right ventricle. They're descending aorta, so it's coming out of the page towards you. This is the spine. This is more lung. Okay, so it's a axial cut, which means I'm going to show you pictorially. It's just like a cut like this. It's like you put me on a sawmill thing, like that. Okay. Yeah, exactly. Exactly. It's just like the person in the box trick. So left ventricle, 3 different vendors. Right? I know which vendors they are. You tell me. We're going to take a vote. Everybody look at those pictures and pretend that you want to make a diagnosis. And your diagnosis is going to depend on, say, detecting some small difference in this signal here, or this signal here, or this signal here. Those are the right coronary arteries, right? And you're looking to see if that's open or closed, right? So that's one diagnostic task. Another diagnostic task, which we would get to, is say, look at the brightness of the signal in the myocardium, here, here, and here, to determine whether or not the contrast got into the myocardium or did not. So I'm going to take a poll now. Who would prefer to use this image to make that diagnosis? Put your hands way up. I want to see what it is. Okay, 1, 2, 3, 4, 13. Who would prefer to use this image? Okay, about 6 in. Who would prefer to use this image? Only one person. 2 people. All right. Okay, can you explain to me why you would want to use this image? Is there any? There is no right answer, by the way. These are all used, and they're all picked by people to use it, but so there's no right answer. It's just like, why did you choose it? Yeah.
I guess looking especially at the bottom where there's contrast, it looks like the edges are crisper. There's like more contrast between like dark and light, so then if I'm having to pick out something
Here.
in the
Here.
yeah, so if
Yeah.
I'm having to look at the coronary arteries and kind of pick out something as noise or if it has a very sharp edge and it's probably calcium.
Yeah.
I would be more.
Yeah. So basically, and this is an astute observation, this edge here, all of the edges in here look really sharp, right? And as compared to this, for example, which looks like a globally kind of smoothed feel to it, right? For those of you who picked this one, why does somebody want to say why they picked this one? Yeah.
So, as you mentioned, it's smoothed out a lot. So that means the noise is less visible because it's been kind of smoothed out. So those couple of white points on the top left-hand side,
Yeah.
they are more visible in the second one compared to the first and third.
Uh-huh.
So if we're looking for things like that, we would probably want to, if differentiate them from the noise.
Right.
So I would go with the second one for that.
So you go with the second one, not for resolution, but for low noise.
Yes.
Right. And that's absolutely correct. It has probably the lowest noise of all three, right? And it has a nice, fuzzy, warm feeling to it because of that low noise situation, right? And this is used all the time. This is a popular scanner. Both of these are popular scanners. So those of you who picked this, does somebody want to say why they picked this one?
Just easier to see. All the boundaries are visible.
Yeah. This one is probably the most honest picture in the sense that it's probably closest to what you get by back projecting the raw data with a fairly broad filter because there's noise, right? You can see the noise. For those of you who are comfortable with noise, it's nice to see it so you know what it is, right? This one, God only knows what they do to this picture, right? They have made these remarkably beautiful edges and really low variance in here, right? So there's some big shenanigans going on here. This is like a depiction of the object, right? But it isn't just simply a back projection of signograms. There's no way. There's some really smart stuff. We tried in the lab recreating these pictures from our data, and we went through 20 different algorithms to try and modify signograms to get pictures that look like this. We could not do it. I have no idea how they do it, and they're not going to tell us. Okay.
I thought the first one had a lot more contrast than the other two.
Yeah, that's a good question. Is to like, if you put a line through this, which would be like the contrast between the myocardium and the blood, or the vessel and the fat and stuff like that. Ideally, all three images produce Hounsfield numbers, which should be accurate. And they, most of the time, I mean, they don't drift away from that. Every vendor will say, if you put water in here, I'm going to give you a Hounsfield number of 0. If you put air in here, you're going to get a Hounsfield number of minus 1,000. If you put contrast at a specific concentration, you will get the Hounsfield unit for that. Right? And so most of the time that's true. But there's a whole bunch of stuff done to raw data, and it's not just filtering, but it's also some kind of probably iterative, amplification of high frequencies that doesn't also amplify noise. So it would be actually an interesting project to take one raw data set and see if you could recreate all three of these pictures, see what they do. Right. Okay, so that's noise. For most of the time, inside the field of view, there is adequate sampling, adequate number of projections to make the picture. When you drop the number of projections, most of the time clinicians will just bulk. They'll say, no, I don't want to see any of these streaky artifacts. And you're saying, yeah, but it's half as much dose. I'll say, well, nope, I don't want to see actual wrong signal. Give me the right signal. And so most of the time we're adequately sampled in all these clinical things. So here's some other artifacts. This is the same patient. And when this scan was done, the technician forgot to tell the patient to do something. And that was take your arms and put them over your head. Right? And so the patient, in this case, is lying with one arm here and one arm here. Right? And those arms are, in terms of the field of view, where are those arms? They're way the heck outside the field of view, right? So they're out here, and not only are they outside the field of view in terms of sampling when you can see them on the detector in those projections, when you're orthogonal to them, the fan beam is coming through here, they're not observed at all. So they just come and go in the data. So in certain views they appear, and then in other, as the thing's rotating, they just disappear, right? So now you have a huge inconsistency in your back projection that, sometimes they're there, sometimes they're not. And so basically you want to get all of the objects that are going to be in the X-ray beam, you want to image those objects. Right? You don't want them to come and go, ideally. So here the text says, oh, sorry, put your arms up over your head, and then all of this streak artifact from the arms goes away. Right? Aliasing Artifact. So this is another artifact that happens with modern scanners that have detectors that are fairly large in the Z direction. So recall for this beam here, this is not L. Okay, L is into the page. Okay, for us in this. So this, the detector is usually designed so that it rotates around the patient, and then this is the Z direction. So the detector I've been showing you in those slides has 256 samples this way. Into the page it has 1,000, right, or 820, but 1,000, 1,000 that way. However, when this thing's rotating around, you can see that in this view, these slices or these rows of the detector are seeing this tissue here. And then when it rotates around 180 degrees, they're missed, right? And so you basically can adequately reconstruct a kind of a football, of shaped thing, as opposed to a cylindrical volume, right? So that's taken into account when you calculate what is my field of view in this direction. This is a very subtle artifact that still causes great consternation, and it's called beam hardening. And I think we talked about this a little bit. If you recall, when the X-ray, do I have a spectrum here? No, I don't. When the X-ray spectrum comes out of the tube, there was a peak at a specific energy, and then it rolled off to whatever the maximum energy you could get from the Compton effect. Then as the energy got lower and lower, the number of photons dropped down significantly. And the reason was we filtered those out with a piece of copper or aluminum such that those low energy photons didn't hit the patient. Right? And some of the filtering is naturally done by the target itself and some by the glass, and etc. But then we put a copper filter in front of it. So in a way, what we've done there is we have taken the average energy of the X-rays that were created at the target, and we've increased the average energy of the beam coming out by getting rid of the low energy photons. Right? The patient also does that. And the way the patient does that is as the beam proceeds through the patient, lower energy photons have a higher probability of being absorbed per unit distance as we go along. And so if I look at my X-ray beam just when I enter the patient, it has a certain energy spectrum. And then 10 centimeters into the patient, the energy spectrum's different. The photons that have survived to that depth have a higher average energy. Right? The grouping. This obviously causes an artifact in imaging, and so so let's look at this phantom, and we have this. We're just going to say what happens at this pixel here for a projection this way, right? This projection along this direction, whether I go this way or this way, it should be the same, right? They're 180 degrees apart, so it assumes, like, convolution back projection assumes that those projections are the same. Right? But when we look at what we actually see, if I look, well, let's look at this one first. The source is here, the X-rays come through. This pixel, its contribution to the attenuation is made on a beam that has seen that depth of penetration and therefore has a specific average energy. When I look at the complementary projection this way, the depth is much higher, and so when that X-ray beam is passing through my pixel of interest, the average energy of that beam is higher. And so those two projections will not be the same, right? because of that effect. This basically, if you don't correct for the fact that the beam is hardening as you're going deeper into the sample, and you just, do a back projection reconstruction and look at your results, you'll have a kind of a hole in the middle of your phantom, right? And this hole is because these central pixels, there's no way a beam hit these pixels without penetrating through a lot of phantom first, right? Whereas out here, there are a number of projections where the beam just sort of went in here, hit the pixel, and came through here, right? And so it had a much lower energy beam. So these guys it looks like their ability to attenuate X-rays is lower because they're busy attenuating higher energy X-rays than the ones out here. Right? And so you essentially compute, given the geometry of what's here, a correction factor and amplify up the central pixels. Right? Otherwise, your water doesn't all have a Hounsfield unit of 0, right? So you do this with, say, a water phantom, and everything in here has to have a Hounsfield unit of 0. Any questions about that? Yeah.
Does that get down to the raw data, to the Fourier, to the G? So when does that occur?
Yeah. It has to have it has to be an iterative process because you have to go back and look at the geometry and say, at what depth, did this occur for that projection, and do the correction for each pixel, right? So to do this, you can imagine you do a first pass recon, and then look at the object and say, okay, how far through did I go? And you can make your estimates of what your beam hardening will be from that lower quality image, right, in order to correct for that beam hardening. Right?
So that you do that for a phantom. How do you do that for a person that is slightly different in size? And so
yeah.
Essentially, does that get? It's the assumption that the same thing is happening for a slightly different shapes, an oval versus a circle, or?
Yeah, it basically, you can do it exactly if you do it iteratively, right? And so you have an estimate of your picture, number one, and then most image reconstruction techniques now make a first picture, calculate things based on that first picture, and then make the next estimate, right? And oftentimes there's a trade-off between that iterative process and the filtering of the sinogram, right? When you look at the object, you say, oh, well, I know this cluster of pixels over here is the following, therefore in my sinogram, I should have smoothness along these lines here, and so you start going backwards and forwards, as well as doing this type of correction, right? This gets really challenging when, say, there's a piece of metal right here, right? And then that gives you a huge shadow behind it, such that all of the projections that hit the metal essentially occlude your vision of anything back here. And so there's just missing data, And so to do that, you have to do an iterative process to find out where's the occluder, behind it. I now know that these views should just not be considered, when I'm trying to figure out what the Hounsfield unit is. Okay. So let's look at, but you know what would be, we do these projects, right, in this course. That would be a really cool project, would be to show how you do that, say just in a phantom. You know, how do you go about doing beam hardening correction, right? It's not easy though. Right? You'd have to make some assumptions about your beam and how you're gonna sample your beam and all that kind of stuff. Okay. So one of the primary things that CT has been used for in the past is detecting lung cancer, right? It now has been shown that low dose CT in smokers, right, who are beyond about 40 years old, actually makes a significant decrease or significant decrease in the number of people that die from lung cancer is if you go to this screening, to low-dose CT screening for smokers. For normal people, well, smokers are normal. For people who don't smoke, it doesn't make a huge difference, right, if you do these screens, because the frequency of the nodules of lung cancer is so low. So there's actually this, it's been approved and everything now that programmatic screening of smokers should occur, right? So you get these lung cancers early. But it's still not a trivial read for a human, right? Is to look at a CT and say, that's a lung nodule versus that's an artery or a vein in the lung. Right, and so here's, 4 of those cases of sort of progressively more difficult calls. Right, this number in the corner is like they do a trial where you just give images to radiologists and ask them to make the call, and they get thousands of images. Right, and they're just like do it, bam, 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 bam. So this number is the number of radiologists out of 13 who actually found that lesion. Right? So 12 out of 13 found this lesion. So that's no problem. 8 out of 13 found this one, because it looks a lot like that thing, which isn't a lesion. 5 out of 13 found this one. 2 out of the 13 called that positive. Right? And for very good reason. Right? As a human observer, are you going to call that positive? I don't think so. You're going to be wrong a lot if you start calling those positive. Yeah.
Do they give reason as to why they chose it?
No. These trials are basically just binary. You just like call it or don't call it. Right? And if you started having a vector of all these reasons and stuff like that, the statistics would get pretty hard. This is where deep learning is going to play a big role in finding things. Yeah?
Do you only call one, or do you call like on the last?
On this?
No, on the last one.
Oh, this guy here?
Yeah, so could the person have called that one and 3 others?
Yeah, I mean, these 2 people that called it positive, maybe they called this thing. Yeah, right? Who knows? I don't know. Yeah, right. You could be wrong and still be right.
Maybe it was whether me.
Yeah. So you could look it up because it's a paper. Okay, so it's right here. This guy's from Stanford, Rubin, and it's a pretty recent paper. The issue with things like this is, for radiologists, this is a hard job to do this, over and over and over and try and pick these things out. You can imagine that if you had a trackball and you were rolling up and down through these slices, that the way that this thing is moving as you roll up and down could be an indicator that, oh, wait a minute, that's not a vessel. That's not tracking like all these other vessels in the field of view. That's a nodule, right? So it's kind of unfair just putting it in a single plane, because when you roll up and down, you can sort of see other stuff. But jobs like this, where anything where a human being, like if you look at this one, where a human being does it in about 3 or 4 seconds, deep learning is going to do that, right? It's just going to take it over. And because you can put 10 million exams in to train the network, and a human can't read 10 million exams, right? They can only read, 10,000 a year. And so the way this will go is you'll have a radiologist and their assistant, which is the deep learning computer for whatever task they're doing, whether it's looking for breast lesions in mammography or looking for these lung nodules. And it'll be like having a radiology fellow who has seen 10 million exams, right? So they'll make a recommendation, say, you know what, you should look at this thing. And then you look through and make the call. So this is, in a sense, a very simple task we're doing with CT, and why you want to image that little fellow there as well as you can. If there's any feature of that thing that makes it different than the background, you want to be able to resolve it. Sometimes it's the edges, sometimes it's the texture, right? And sometimes it's how it moves as you zip through. So that's why we're trying to do these things. So here's a standard X-ray attenuation image of a lung field, and you look at it and you say, there's something different about these two fields, right? Can anyone tell me what's different about the grayscale of these two fields? It's not a trick question, right? So just the background here seems a little brighter, right? Right, so the mean value back here looks a little brighter than this, right? Yeah, it basically, there's something in there that's causing attenuation that isn't over here, right? And what you can do is by taking images at different energies. Okay, so if I take an image that's an 80 kV X-ray image and see what the attenuation is at 80 kV, and then I take a brand new image at 120 kV and look at the attenuation at 120 kV. The way the change of attenuation occurs will be different for different tissues because they'll have different energy sensitivities. And so you can then start to isolate materials in the field of view. And you can do this to, say, isolate iodine. So what we're really interested in is making a map of iodine concentration, because we inject the iodine and ask, where does that stuff go, right? So it's been basically filtered out of here, but inside the lung field, this is a map of where the iodine went inside this lung background. And so you can see there's a lot of it over here. So this lung is being perfused okay. There isn't much over here at all, right? So especially up here, the lung is not being perfused. So blood just is not going to that chunk of the lung, okay? And so this person has a very massive pulmonary embolus. Like there's some blood clot that is in an artery that is preventing blood from going into their right lung, right? And so it shows up instantaneously like that. If you're a very skilled reader, you can obviously see this, but as it gets more subtle, it becomes more and more difficult. And so dual energy can help in those situations. And you can imagine dual energy can be used for a lot of things. And that would be another really cool project, is to look at depiction of, say, calcium with dual energy versus single energy X-rays and CT. So here's just an example. You have what is the signal intensity, at basically different energies, and essentially what happens is at 140 kV, as my intensity goes up, the I value or the image intensity in that image goes up at a different rate than it does at 80 keV. So that gives you a unique slope for this substance versus bone versus soft tissue. And so that's how you can differentiate between those things. Okay, so since this is apropos for today, since we talked about sampling, there is a manufacturer who has taken their normal two-dimensional detector array, which in their case is 320 by 1,000, right? And they've said, well, let's just go, to 640 by 2,000. Well, actually, what they did was they cut the thing down. And so they essentially doubled the resolution in two directions, in the z direction and in the theta direction, or along L, right? So they've got 4 times as many pixels. They got a lot more data to process. And the question is, can you see anything with this high-resolution detector that you could not with a normal CT detector? And it turns out, yeah, you can. So this is the, say, a lung nodule, right, here, at a normal CT resolution. And this is what it looks like with this high-resolution CT scanner. It looks like this. And so the details are sharper. Obviously, you could see it here. So the detection isn't the issue here, but it just shows the higher resolution image, the ability to see things with higher resolution. So one would assume you're going to detect smaller things, but that has to be validated with an actual experiment with humans looking at this. Because this just doesn't come for free, right? You need to more than likely use more X-rays, right, in order to get enough counts in this larger number of detectors in order to produce images of sufficient signal to noise. So it's not free, but it gives you that opportunity. The other thing that had to be done when you say, oh, okay, well, I'm just going to double along the L direction. I'll just double my number of projections or of samples, and in the Z direction, I'll double them, and then I'll have to take twice as many angles, right, to get the sampling right. The spot size that creates the X-rays now has to be sort of on the order of this dimension, right? We can't have a 2 millimeter spot size and a 250 micron detector over here. It doesn't make any sense, right? We would just see a blurred picture on this detector. So now you have an X-ray tube that has really small spot sizes. It's like a quarter of the area of the previous X-ray tube. And we want to get more X-rays out of it because we need to fill up these detectors and do twice as many angles, right? So it's one manufacturer has gone down this road. The others have basically let them have it because they're like, nah, that's not going to work. It's just not going to happen because they do it scratch it out on their whiteboard with the engineers saying this product will not go anywhere because you need too much X-ray dose. This tube will be blowing up all the time, blah, 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 right? So usually one of the manufacturers has to extend their neck out and do something like this and then show that it actually works such that the customers come back to the other manufacturers and make them do it too, right? This manufacturer, by the way, was the first one to make a really wide detector in Z, right? The others had detectors that had 64 slices. These guys went to 320 slices, they went from 128 to 320, and then a couple of manufacturers followed them. So they have guts. It's really cool. It's a lot of money, right? You build this thing and put it together. You're talking, hundreds of millions of dollars to make this work, and then if it doesn't sell, you got issues. Right? So there's the 2 pictures, and look at that. It's fantastic, right? Look at these little airways here. You just don't see them over here. Now you can track airways, down to tiny little things. And so the issue now is like, it's up to your imagination what it is you're going to diagnose with these pictures that have this crazy resolution, right? And so that's, a lot of physicians aren't that imaginative. They work hard, but they're not that imaginative. But it takes a couple of thought leaders to say, oh, now I got this machine, I can do the following. That same machine can be used, although it's a little tricky, to do cardiac imaging. The reason why it's a little tricky is because the gantry itself can't rotate as fast, because we need to build up the X-rays on this detector. There's so many detector elements. So in order to build up those X-rays, we can just slow down the gantry and get more X-rays through. Right? So this gantry right now, when this image was taken, was rotating at, I think, a half a second per 360 degrees, which is about half what a normal cardiac scanner runs at. But ridiculous pictures. You look at the detail of the valve here. Let me go back to my arrow. So if we go through here, look at the aortic valve leaflets, and then there's these tiny pieces of calcium on the aortic valve leaflet that are detected. Let me pause it here. Right there, right? That's not going to show up on a regular scanner. So you're seeing things way early. You come down, up here. That little ditzel right there, right, is a piece of calcium, and this is a soft plaque that would be very, very difficult to see on another system. So you're also seeing these really tiny things quite early with this high resolution. And look, you've resolved the wall of the left atrial appendage. So see how there's an edge right along there? I've never seen that in any other CT picture than this one, right? This is the wall thickness of this object. That's pretty cool. Now, this person held their breath very well, had a really low heart rate, and so everything was good. A lot of people that have heart disease aren't like that. They're going to be moving, and you're just going to have to use a normal scanner. But crazy good pictures. This is what, if we focus on one of those pieces of calcium, not the one I just showed you, but one further down the left anterior descending artery, this is what it looks like on that high resolution scanner. This is what it looks like in the same institution on a competing scanner that has kind of normal detector resolution. Okay, same person. Remarkably consistent looking pictures, right? These were like 6 months apart or 4 months apart or something like that. But this slice looks like, kind of identical. And that's what this looks like over here. So, you're going to see stuff over here you're just not going to see here. Okay, so that's it for today. And I will have the new problem set posted by the end of today. And then in the next, so Monday, we'll look more at some advanced applications of CT. I can answer questions as we roll up to the quiz. And then is the quiz on Wednesday? It's Wednesday, right? Yeah, so the quiz is next week, Wednesday. Okay. Oh, yeah, I answered that message.